just double check. Great. Yeah, for people online, just to introduce myself, I'm Dr. James Craggs. I'm an aquarium curator at the Horniman Museum and Gardens in London, but also a co-founder of the Coral Spawning Lab. So I'm going to talk a little bit about the role of co-culturing herbivores with corals as a way of boosting productivity. So yesterday we talked about land-based spawning and the different methodologies that we can use from that. Today I'm just going to focus a little bit about the increasing productivity that we can gain from co-culturing corals with herbivores. So ultimately, just thinking about coral production, we've learned a hell of a lot over the years. We know a lot more about different spawning behaviors of species, embryo fertilization techniques, embryo rearing techniques are all improving. But the challenge we have is there's die-off going right the way through, or mortality occurring right the way through different stages of their life cycle. That's partly because corals have a type 3 survivorship curve, unlike humans, type 1, where they're producing millions and millions of larvae, and very few of those are actually making it to adulthood. So really trying to understand where these bottlenecks happen on the coral's life cycle, we need to kind of develop different techniques to boost productivity and try and remove some of those bottlenecks as much as possible. And certainly thinking around post-settlement bottlenecks is one of the areas that I really wanted to look at. How can we increase those number of corals living after they've settled? We all know that corals and different benthic algae competitions are really negative for juvenile corals. They're very small and weak to defend themselves and create a platform on the reef. So we see lots of these negative benthic competitions, things like Peysonelia algae, different filamentous species. The filamentous species of algae then bring in sediment. That sediment then allows things like cyanobacteria and diatom growths, which ultimately open up infection and kill these juvenile corals. Not only that, but we know that crustose coralline algae, or the biofilm and the bacteria associated with crustose coralline algae is one of those triggers to allow metamorphosis. But crustose coralline algae absolutely do not want a coral living on top of it, and different species has lots of different mechanisms of getting rid of those corals. Some of them, this is a species that predominates in my systems back in London, and it's really aggressive. It just, as soon as the coral settles, it will ramp up into overdrive and just completely engulf the juveniles. Other species will slough off layers, so the coral that settle on an epithelial will just slough off and the corals disappear. So we need to be tackling some of these benthic competitions if we want to boost up the number of corals produced. Now, Sander mentioned this from an aquarium point of view. When we run public aquariums or home aquariums, whatever that might be, we often buy something called the cleanup crew. And there's different animals that we employ in an aquarium to deal with a lot of these algal species, whether they're snails, crabs, urchins, fish. Each have their niche and will eat different types of algae. Now, urchins are indiscriminate grazers. They bulldoze everything back down to bare rock. Their rasping beak, they can deal with all of these algal negative interactions. The challenge, so one of the things I started to think about is, could we co-rear corals with urchins? Now, the challenge with a big urchin is it's got this beak and it will literally eat, whether it's doing that intentionally, we don't really know that answer yet, or whether it's just accidental grazing and damage those juvenile corals. So it got me thinking, well, could we start looking at co-culturing but using microherbivory? So could we spawn urchins and rear those with juvenile corals? So could we still get the positive effects of the urchins being able to control all those negative benthic interactions and then boost up the coral numbers? And so hopefully these go play. Yeah. So we started working backwards. It took us a couple of attempts to figure out how to spawn and rear sea urchins. So we work predominantly with Maspelia globulus. It's a broad Indo-Pacific species. And we ultimately had a point in time that we knew our land-based spawning was going to be. We started working backwards a couple of months before to start rearing the sea urchins. And the idea being, we wanted to get them through their pelagic phase, settle them, and then grow them to a size that would be appropriate, and that would then time up for when the corals spawn, and we could then introduce the juvenile corals with these juvenile urchins and have this little microherbivory going on. So, you know, like I say, it took a couple of attempts, and then we got the first batch of settled, produced a few hundred urchins, and then ultimately ran an experiment where we had, you know, a control with no grazing, and then looking at different grazing densities. And so I picked the highest grazing density from a paper in Hawaii that basically had 75 urchins per square meter. So that was the upper high grazing density. And then right the way down to 17 urchins per square meter. So these were set up in you know, a randomized design in 10-liter aquariums, and then ultimately tracked out over a 6-month period the influence of those grazing pressures. And the results were absolutely beautiful. The more urchins we put in, the higher the survivorship of the coral. So we ended up with an 8-fold increase in survivorship of the coral in the highest grazing density. And not only that, we found much better growth. So here in A, these are 2 pictures of 6 months old, and this little coral in the middle here in the no grazing control is just using all of its energy to try and fight off the boundary layer and the algae that's trying to invade it. But in the highest grazing density, you know, the coral can just put all of its energy into that growth and establishing itself. And one of the things we know about the corals is there's a size dependency. Once they hit a certain size, that mortality starts plateauing and they become established. And the whole idea of this as well is, you know, can we use nature-based solutions rather than you know, humans going in there with toothbrushes cleaning around corals? You know, it's just when you start scaling this up, it's just you can't put the number of man hours to it. So can we use these nature-based solutions to do the job for us? So we got much higher growth, we got better survival, but it then also has an impact on the urchin's growth as well, which makes perfect sense. You know, in the lower grazing density, there's just more food, and so they can grow quicker. When you load up in the high density, the urchin size just becomes stunted. So when we're thinking about the number of urchins we want to produce with this co-culturing, it's also understanding that sort of interaction that happens with the size of the urchin itself. In the early stages, we were just using one species of phytoplankton, and we've done a lot of work now in our phytoplankton culturing facilities, where we've broaden the range in essence of it. So to begin with, we were using Tysocrysis lutea, and we had sediment took about 21 days in this species. So it's actually much longer than it should be. It's much quicker than diadema. It's quicker than the Trypnusi species. But then as we started increasing that nutritional profile of the different phytoplanktons, we significantly shrunk the pelagic phase. It's a really cool Pluteus swimming around. So we could shrink the actual pelagic phase, which meant that, you know, there's less staff time to actually rear the number of urchins we need. We've tried lots of different culturing techniques over time. Each species has its own sort of requirements for culturing. Maspelia is actually quite a forgiving species. You can culture these in just completely static bowls. They're very active swimmers. So after 24 hours, so with an urchin, it goes through its larval phase in the first 18 hours, and then it enters the Pluteus stage, where they're actively swimming. With Maspelia, they will literally just pick themselves up and swim around. So you can do them in a static bowl, put into in a water bath. And these are the original designs. We're using Artemia cones, which often are used for coral embryo rearing as well, and then try different static bowls versus bowls with bubblers and what have you. you end up with quite interesting development of the arms. It's very plastic. So the more static the water movement, you get these longer arms. If it's high flow, the arms shrink. And the thought is it's all about the back eddies of improving feed efficiency. And there's been a lot of work looking at urchin plasticity of growth over time. Hopefully these are going to play. So I've left the noise on this. So ultimately, this is the master, Skip Moe. He wrote the book, and it literally is the book, the Diadema Culture Manual. So he started writing and working with diadema culture in the 80s, 90s, produced this book, I think last year, the year before, and Skip has helped so much with the husbandry for us in how to do this. So we have had a similar system that he made, built. It's a chrysal with a flat back to it. So a chrysal is like a jellyfish tank, and it's just trying to create pelagic water movement. So it's a bit like a washing machine with this gentle water movement going around. Now the thing with, he designed this based on diadema having these very long arms, and they act like a glider. Now the problem is, if you, or the theory was at the time, Alwyn's showing something different now, right? That if you created air movement the whole time, you would just end up breaking these arms off, and then they wouldn't be able to glide, and they would die. So if I play this video again quickly, what we have is a spray bar in here, and it's on a timer. So that's the air kicking in, and it kicks in for 4 seconds, and then it turns off. And the idea is it then slows the growth, the flow down, and then it kicks back in again, and then pushes the movement around. So you're creating that open ocean without creating the shearing forces of the air that's bubbling up from it. And we found this so productive in the way that we now culture the individuals. We do the same method of using a warm water bath. We call it heat shot, but it's much nicer calling it a warm water bath. Generally, with Maspilia, it's quite cool. The females have a very different behavior to the males. The males are just releasing the sperm out, whereas the females really extend their tube feet and kind of have this rhythmic pulsing where they're throwing the eggs out into the water movement. So we will generally isolate each individual. So we've got 2 males here, and these are all females. And we culture probably every 2 months. We're just constantly producing urchins. This last batch, in this one single tank, we got between 500 to 1,000, something like that. So they're very productive, but they are a much easier species than diadema to produce. So we use this predominantly for co-culturing with corals for any experimental work we're doing, but we've now developed a relationship with University College London, and we produce a lot of larvae and embryos for their CRISPR-Cas9 and genetics work. So it's sort of broadened the type of research that we're doing or collaborating with, so which is pretty exciting. So I published that paper as part of my PhD, and at the time sort of started thinking about this circular economic model again. How do we bring income into restoration? And one of those potential routes is the aquarium trade. If you're co-culturing, could you co-culture urchins? Once they've done their job, could you sell those into the aquarium trade or potentially use them for a restoration tool? But then started hypothesizing, what if we used Trypnesis gratilla, that's again as a broad range Indo-Pacific species, and it's eaten a lot for the uni that it produces. So we started culturing this about the same time, I don't know, 5-6 years ago. It is a harder species to rear than Maspilia. But we then applied for a grant. We got it in 2019, and then COVID happened, so we gave that grant back. We then reapplied, and we got that last year from the European Union of Aquarium Curators. It was a small seed grant, and it was working with Palau, in Palau, with Pickerick, with a view that could we start these principles of co-culturing to produce higher numbers of corals for restoration, but once those urchins have got to a certain size, could they come into a side aquaculture facility to be sold into the human food market? And Palau is the perfect place to do it because it is so heavily overfished, both for a food commodity in country, but also selling it out of country. So with that pilot study, we had a little space of on the roof here above. This is above the public aquarium, and then the research facility is over here. And so we designed a little phytoplankton and urchin culturing facility in an office block with probably the best view in the world out of any office. And then my deputy, Hartley, went out and spent 4 weeks basically putting this into action. And so, again, there's the facility, and then he's built this lab with phytoplankton culturing and using, again, the cones for culturing vessels. I think we'll probably apply for more money and then look at getting the chrysals out there, maybe even working with you and see if we can get some of the other devices out. So this was finished about 3-4 weeks ago. They've managed to do the first spawning, not got any rearing yet. So the plan is that this has created the initial infrastructure, and then colleagues from both Newcastle University and Pickerick have won a very big grant that will span 3 years, working with the local community to start using these as tools to develop these concepts further. It's really interesting, all the settlement media. I was on holiday with my family down in the southeast of England. We're on a dry ski slope. I was like, this is the perfect settlement media to stick in the ocean. So I asked the guys if they would give me a little off-cut of the dry ski slope. And these got cut and taken out to Palau. And they're going to try some of the work that you've been doing. So exactly the type of thing that you've been doing is exactly what we need to be doing in Palau to work out where these natural recruitments are as well. We've been reading a few papers recently. Using Nitsia is a benthic diatom, really helps settlement. And so the idea behind this, we want to inoculate the ski mats with benthic diatoms and then put them out and see if we can enhance settlement using that sort of preconditioning. A technique that we've been using with the Mespilia over the last few months as well is also using the feces from the adults. So there's been some really nice papers published showing the microbiome from the feces of the adult is a really important attractant to bringing the juvenile urchins in. So going back to the Mespilia, just as we see the rudiment development in the 8-arm stage, we'll actually put an adult in there and just let it poo all over the place. And it really seems to have worked very nicely with that. So again, we'll be trying that with Trypnoces. And what's great, many others have been picking this up as well. So Joe is a good friend, part of his PhD, working with Josh and Aaron, looked at co-culturing with cervicornis, but looking at gastropods in that. Rachel Neal, her whole PhD, has taken this a step further in Australia. And she's been doing some amazing work, really broadening the different types of herbivores that you can co-culture with. She even tried it with crown of thorns juveniles, to see whether the herbivory stage at a young stage could actually act like a co-culture. It absolutely did not. It killed all the corals. And then recently, last year, this paper was published out in Hawaii using that co-culturing technique for restoration output. So again, using Trypnoces gratilla, we've spoken a lot with colleagues in Hawaii. They are producing tens of thousands of Trypnoces as natural biological control to try and reduce some of the macroalgal growth in Haniona Bay. But what about the fish? So certainly the stuff that James Guest and co out in the Coral Cyst have found that you're creating these ocean frames around the juveniles in situ nurseries plays a massive role in improving their growth and survivorship. So the mesh frame allows juvenile parrotfish to come through, but excludes those larger ones. But the next challenge for Reef Reefs is, how do you broaden that out into multiple herbivory? Because, just thinking about how complex these ecosystems are, this multi-trophic aquaculture is got to be a very important role to play, I think. So the next thing we kind of led on from that co-culturing is then thinking about heterotrophy with corals. Could we add additional gains to those survivorship by co-culturing, but then start manipulating the feed of the juvenile corals? And there's lots of papers published about the important role of heterotrophy at multiple different stages of life. I think Peter Harrison's group published a really important paper last year or the year before looking at larval feeding. You know, at what point do we need to be feeding these corals? And they showed incredible increase in settlement success when they blended up artemia and fed that into their larval cultures. So there's just still so much we need to study and understand, and you know, how can we apply these to get increased gains? There's also interesting evidence to look at heterotrophy and how heterotrophy provides increased thermal resilience. So one of the studies we want to look at is, could we build on this, but also not thinking about thermal resilience from a genetic point of view, but thinking about it from, you know, a nurture rather than nature point of view. So what we did is we spawned Croppa mediapora. We didn't do pairwise crosses. We created a mixed pool of genotypes so that we had a mixed group of fully related, half related, and mostly unrelated offspring. Those were settled on 500 frag plugs. We basically then were looking at different feeding densities. So no feeding, using Tysochrysis or phytoplankton, rotifers as zooplankton, also a commercial diet, and then using 9 urchins because we didn't produce enough on that year. We know they're voracious predators, so you know, we created this randomized design and then tested that. So from the day they were settled, they basically got isolated every day for 2 hours for 18 months and fed a different diet each day. After about 6 months, the actual survivorship wasn't anywhere near as good as we were hoping. So we actually didn't really see a statistical difference between the survivorship from the control and the different heterotrophic feeding. But I think our data is masked, and I think it's because basically we massively oversettled. So in the co-culturing study, I settled about 2,000 recruits or spat. Here we were over 7,000 for the same number of plugs. And what we know is there's something called density dependency survivorship, that there's this sweet spot of settling the right number of corals. If it's too few, they don't live. They then have this beautiful sweet spot, and then if you oversettle, you just have this allergenic competition kicking in, and actually you lose way more of them. So it's another factor, and it's a very difficult thing to predict because you can never say, I'm going to get 10% settlement. You know, it's such a moving target, so you end up back calculating it. But you say, right, I've got X number of plugs, let's aim for 10% settlement, and then we can calculate the number of larvae we need to put into those settlement things. We just got carried away and chucked far too many larvae in, basically. But again, looking at the density from the papers, you know, you really don't want to be going any than 1.5 spat per centimeter square. So it's actually not very many when, I mean, some of them you couldn't even see the plug. There are so many corals on them. So, you know, we did improve the growth. So while the survivorship wasn't improved, the growth was improved. From that, we basically then started cutting these individuals up to maximize the number. So where we got multiple corals on a plug, we cut those up. And then after that, we then created thermal stress events. So after about 18 months, I've put it at 12 here, but it was slightly later, we put them into a thermal stress system and then sort of simulated different thermal anomalies to see the influence of different heterotrophy. What we find is that the phytoplankton, actually, we got a higher Symbodinium AC density, the same is true of the chlorophyll. And we actually have a much better improvement in the number of degree heating weeks that we start seeing the early onset of bleaching. So heterotrophy is providing some additional resilience to those recruits, which is a positive thing, I think, an encouraging thing. And then basically the point at which we kill the corals also is further exacerbated or pushed back with the heterotrophy. Interestingly, the commercial diet did the worst out of all of this. So again, potentially new tools or principles that we could put into you know, an aquaculture process, whether that can be tailored and used in situ, but to try and give these corals and these recruits an early boost. So just in summary, you know, we working with this co-culturing. It definitely improves sort of staff time and labour. There are, I genuinely think, huge potential gains and opportunities to look at these circular economic models of really changing the way that we think about restoration and how can we use these nature-based solutions and sort of powers of economy. And then heterotrophy, as you know, it's confirming lots of other papers, but done in a slightly different way, that it can also boost these thermal resilience. Again, thank you to you know, lots of scientific partners and people that support it. Thanks for inviting me out here, and thanks for Rotterdam for sponsoring my trip here. Skip Moe, absolute legend in the urchin world, and thank you for listening.
No questions?
So I was wondering, Jamie, your first sort of co-culturing experiment that you showed, where the higher density urchins resulted in the highest growth rates.
Yep.
Did you see any damage with the lower density urchins on the corals because they became so much more bigger? I can imagine that they would also start raising the corals.
Not at all. Not with Mispilia. It's a much more gentle species. In my initial sort of plans, I was trying to do diadema. So we were working with Diadema setosum, and I just couldn't culture them at the time. I did buy in some. Like I asked the supplier to get the smallest ones. I did try settling some and putting those in, and they ate them all overnight. So they were probably, you know, too big at that size. They were, you know, a couple of centimeters in diameter. But yeah, they did eat all of the spat. So it feels like if you settle them with the microbial, they just grow up at the same pace.
Really small.
But I think also Mispilia is a much milder species. You don't ever see them predate on corals in an aquarium setting, whereas Diadema setosum, they can get a taste for corals, and they'll start munching away on them in aquariums.
Well, we did this experiment with high density, low density. Your low density was 17 scarcity per square meter, right?
Yep.
Which is still your low density, but compared to nature is an extremely high density.
So,
I believe, right?
well, I mean, I used this paper in Hawaii, and that is basically in line with what they were finding in that paper, which is high.
It's a very high.
Very high.
Right?
75 per square
exactly.
meter is what they were.
In nature, normally you don't have, right, 75 square meter. You see, if I correctly understood, you foresee any application in seafood, right? From that.
But that data was from Hawaii. That's the density that they found in the wild. Yeah, on the reef.
Wow.
Yeah.
Wow.
With trip mucics, yeah. So.
I'm impressed. Exactly.
Yeah.
I was like exactly how I thought it was completely.
No. That is wild data in Hawaii. Yeah.
Wow.
Which is nuts.
Yeah, exactly. Yeah, we're already for more.
Yeah.
I think you already answered it a little bit, but I think it's one for the three of us with the already included. If you would put in too many herbivores in the wrong stage, you could basically also undo the coral work that you do. And do you already have a perspective on how that influence can be in situ, or?
I say again. So in terms of the.
If you imagine that you are 1 meter and your solution
All right.
also scrape up corals.
Yep.
And you will do it in situ. Do you already know the correct balance? Because I think then it could also be if you overstock your
My gut feel is that it will be very much a species dependency relationship thing. Like I say, Maspilia, they don't eat corals anyway. Other species of urchin, 100% they do, and they probably are not the right ones to be working with. And there's lots of papers published that actually Diadema antillarum will eat juvenile corals, 100%. But it's just the overall positive effect of controlling all that macroalgae, that actually the corals that are settling in the crevices away from the grazing of the Diadema antillarum are the ones that actually recruit into the system. But those that get settled on the flats are just eaten anyway.
But could it then be that we end up with seasonalities also in when it's best to start corals and grazers? Because that's one thing that I'm always wondering myself. Many things, because it's also sometimes, how do you say, run as a business. You go whole year through, and couldn't it be that seasonality in both corals and grazers is also a thing?
A driving factor.
To put it in.
Yeah,
otherwise we could influence the work of our partners, and we don't want to do that.
No, sure. I mean, I don't have an answer to that, if I'm being honest. I guess no one's tested putting them out of season, and that's the next phase of it, right?
Thank you so much. We appreciate